Thank you. My name is Jacob Schreiber. I'm a fourth-year graduate student and NSF Big Data Fellow at the University of Washington, where I study the intersection between machine learning and genome science. I've been working on Pomegranate as a side project for the last few years, and I've recently been spending a lot of time on it, so I'm really excited to be talking to you about it, even though I think my advisor would have preferred that I was working on research instead. But before we get into that, I'd like to talk a little bit about my journey and how I got here. I started off as an undergrad at the University of California at Santa Cruz, where I was working in a research lab that recently came into a lot of data and didn't have any data scientists in order to analyze it. So I capitalized on the opportunity, but I very quickly ran into a problem that I'm sure many of you have encountered. I needed an implementation of hidden Markov models, but couldn't find one that both had all of the features that I needed to be able to be installed, needed to have, and could be installed. So instead of struggling with all the dependencies of these various packages and these error messages that I was getting, a colleague of mine and I decided that we would simply write our own package, and this became known as YAM, or Yet Another Hidden Markov Model. I then started my graduate school at University of Washington, and I was taking a year of machine learning classes. Apparently, mixture models are very popular in these introductory machine learning classes because in each of the ones that I had to take, they asked us to implement this. Instead of rewriting all of this from scratch, I realized, hey, a hidden Markov model, like I had implemented for YAM, has many of the components of a mixture model. So instead of rewriting it, I'll simply just take the components of YAM, reorganize them, and then submit that as my homework assignment. This is where Pomegranate started, out of graduate student laziness. So I then had to do other things like implement Bayesian networks, and I realized that all of these different probabilistic models that they had us implement were really just shuffling the components around for each other. And so I started to put these things on GitHub because open science is apparently good, and from then it's just continued on. In the summer after my first year, I did an internship with the Scikit-Learn team in France. It was really there that they taught me a great deal about Python and how to get bare bones efficiency out of my models, and also how to release the global interpreter lock in order to do multi-threaded training, features that are now prominent in Pomegranate. I was working a lot on the gradient boosting implementation for Scikit-Learn and was able to speed it up along with all of the other tree-based implementations a great deal while I was there. I was fortunate enough that earlier this year they asked me to join the core development team, so now I spend every morning replying to 30 to 40 emails that I get on issues that are opened. When I got back, I was lucky enough to be supported by the eScience Institute through an NSF IGERT Big Data Fellowship. They provided me with money in order to work on data science-related tasks, and really they helped me focus my development on Pomegranate not so much on just developing another tool for small to medium-sized data, but how to consider large data aspects, how to consider scalability, how to consider more data that can fit in memory, how to consider the parallel implications of what we're going to be doing. And then I sold out and worked for an oil company the next internship, and the remarkable thing about it was that conversations that I had there led to research on Bayesian network structure learning that allowed me to get a publication, which made my advisor happy, but also is included in Pomegranate. And I hope I'll have a chance to talk with you about it towards the end of this talk. If you get only one thing from this talk, I want it to be this. Pomegranate is more flexible than other packages, faster, is intuitive to use, and can do it all in parallel. It sounds a bit haughty, but I'm hoping that I'll be able to convince you that it's true by the end of this talk. So, to dive right in, there are 6 main probabilistic models that are supported in Pomegranate. The first are basic probability distributions, like the uniform distribution and normal distributions. Then we have mixture models, where you're combining multiple of these distributions in order to form a more complicated one. We have Markov chains, hidden Markov models, Bayes classifiers, and Bayesian networks, of which I'll talk a little bit more about here. I have 2 helper models as well, implementations of k-means plus plus and scalable k-means, as well as implementations of factor graphs. These can be used by you if you want, but they aren't as feature-rich as the 6 main models. They're mostly there to support the algorithms of the main models. Yeah. So, one of the core tenets of Pomegranate is that all of these models, despite seeming like they're very different, are in fact just probability distributions. A normal distribution is a common distribution that we have. A mixture is just many distributions that form a more complicated one. A hidden Markov model is just a distribution over sequences, and a Bayesian network is literally a probability distribution that's been factored along a graphical structure. While these lead to complicated different algorithms, they can all be treated the same way. And if they can be treated the same way, there's no reason why you can't stack them within each other. So this plot shows the ways that you can stack models in Pomegranate currently, where the rows correspond to various models and the columns correspond to which model you can stack them inside. Of course, basic probability distributions make up all of the other more complicated models, but you can do things that other packages don't allow you to do. For example, we're all familiar with like a naive Bayes classifier, which is a simple one, but typical Bayes classifiers can be composed not just of basic probability distributions, but also of mixture models or hidden Markov models. If you create a Bayes classifier that uses hidden Markov models as the probability distribution instead of, say, a normal distribution, now you're creating a classifier over sequences automatically without any type of algorithmic difference. This is different from many other other packages which implement specific models. For example, Scikit-Learn implements Gaussian naive Bayes or multinomial naive Bayes. But in Pomegranate, you can just drag and drop any type of probability distribution to create, say, an exponential naive Bayes, or have different distributions model different features as appropriate. Since all of these models are really just the same idea, a probability distribution, this is the entire API right here. That you have the basic calculating the log probability or probability of a sample given the model. You can sample from your model. You can fit a pre-initialized model to some data. The summarize and from summaries methods implement the out-of-core API that we'll talk about in a little bit. The from samples method allows you to do things like structure learning or initialize using k-means or something. It's more analogous to the Scikit-Learn fit than Pomegranate's fit is. And then the compositional models allow you to predict proba, and predict log proba in the exact same manner that Scikit-Learn allows you to. There are many distributions that are currently built into Pomegranate, but you can also build your own custom distributions and allow them to work. I've highlighted in red the ones that I think are the most relevant, the ones that are the most used. You have Bernoulli distributions over binary data. You have normal distributions, which are classically used. You have discrete distributions over categorical data. And then for multivariate distributions, there's the multivariate Gaussian distribution that's commonly used, and independent components distribution, which allows you to model each one of your features using a different independent univariate distribution. So let's jump into the claims that I made at the beginning. The first is that Pomegranate can be faster than NumPy. If we want to fit 10 million samples with 10 dimensions, we want to fit a multivariate Gaussian. Using NumPy, we'd first extract the mean, and then we would extract a covariance matrix. In Pomegranate, what we do is we just call the from samples method using the multivariate Gaussian distribution. It takes around 20% less time in Pomegranate to do it than in NumPy. At this point, you may be wondering, but wait, doesn't NumPy use BLAS internally, which, for those who don't know, is essentially just computational magic to make things go fast? This is true. NumPy does use BLAS, but so does Pomegranate. And in fact, Pomegranate uses the Cython bindings to BLAS, and so you don't have to convert back and forth between the Cython layer and the Python layer in order to get this computational magic working. In addition, Pomegranate calculates the mean and the covariance matrix in a more efficient manner than NumPy does. Recently, I also just merged GPU support for multivariate Gaussian distributions, and it seems as though this is providing around a 3 to 4 times improvement using the Tesla K40 GPUs. On the left-hand side, what we have is speeding up a multivariate Gaussian distribution. We have the fit function here, which is around 4 times faster. We have the log probability function here, around 4 times faster. And then since Pomegranate is built in such a modular fashion, without any additional code changes to the mixture models, you can accelerate them using a GPU. Here, this is the fit function for the GMM without any changes to the code. Here's the speed up using the log probability function. One of the other reasons that Pomegranate is faster than NumPy is because it uses these additive summaries, these additive sufficient statistics in order to calculate updates to its parameters. For example, for a normal distribution, what we want to calculate is the mean and the variance. Instead of going through once and calculating the mean, and then going through again and calculating the variance, which also requires you to calculate the mean at the same time, you can calculate both at the same time. Here, if we only store the sum of the weights, the sum of the weighted points, and the sum of the weighted points squared, we can exactly recalculate the mean and the standard deviation. All models in Pomegranate allow you to do this, whether it's a normal distribution or a multivariate Gaussian distribution or a hidden Markov model. All of them use these additive sufficient statistics to calculate model updates. This has a natural implication, which is that if we have these additive sufficient statistics, we don't need to see the entire data set at the same time. What you typically would do with like Scikit-Learn is that you would have some big data set and you would look at it and you would calculate new parameters using it. Recently, in this era of big data, it seems as though we have a lot more data, a lot bigger data sets, and when we try to load them into memory, we get an out-of-memory error. Unfortunately, out-of-memory errors aren't good parameters for your models, and typically, you would then try to do some sort of subsampling in order to get it to fit. What you can do in Pomegranate is simply load up batches of data, extract the summaries, the sufficient statistics from them, and just keep going, storing only the sufficient statistics, which is some small set of numbers. Since these are additive, you can just add them together when you're done and get an exact parameter update. This is the exact update, meaning it's the same thing as if you had seen the entire data set at the same time. This isn't an approximation. This is because Pomegranate has separated the calculation of sufficient statistics from the parameter update step. If you do that, there are a lot of other things that you can do. For example, you can do mini batching. If you extract the sufficient statistics from a batch, there's no reason you have to wait until you've seen the entire data set to calculate new parameters. You can extract sufficient statistics from a batch, calculate the new parameters, use these new parameters to extract sufficient statistics from the next batch, and just keep going. Using mini batching has some nicer convergence properties than using the whole data set, and frequently you can cause your model to converge faster than if you're waiting around to see the entire data set at the same time without losing a significant amount of accuracy. This also gives a natural way of doing data parallelization. If you, instead of loading up one batch, you load up multiple batches, assign each batch to a different core, have that core work on extracting the sufficient statistics, wait until you've extracted the sufficient statistics from all of them, and then use those to calculate new parameters, you can get a fairly easy way of updating your model in parallel. And all of Pomegranate's models support multi-threaded parallelization using this scheme. Lastly, and kind of unintuitively, this gives you a natural way of doing semi-supervised learning. This is the task essentially where you have some labeled data, but you have a great deal of unlabeled data. A classic example of this comes from computer vision, where you have a whole bunch of images. And this is what frequently happens in academia, where you have some graduate students, and graduate students typically don't like having to label images all day, every day for the rest of their PhD. So maybe you can get only a few hundred or maybe 1,000 labeled images. But you have all of Instagram. And if you don't know, your pictures on Instagram are being used by researchers all the time. So it's a little bit of a biased data set because most of the pictures on Instagram are either pictures of food, cats, or random landscapes. But these are still useful sometimes. And the idea is that you want to leverage all of the features that are used in this unlabeled data set, like Instagram, in order to improve your model more than you could simply with the hundreds or thousands of labeled data. Here's a simple example. Let's say you have a whole bunch of unlabeled data in gray. You have these labeled points, magenta, red, and cyan. You'd like to use all of this data in order to efficiently learn a model. Some people might just throw out the unlabeled data or throw out the labeled data, but you want to use both in order to create a good model. The way that this works is that you use maximum likelihood estimates in order to extract summaries from the labeled data as you would normally, and then you use expectation maximization to extract summaries from the unlabeled data. These are the respective algorithms for doing supervised and unsupervised learning. Since these are additive sufficient statistics, there's no reason why you can't add them together in order to get the new parameters. This gives you a way of leveraging both your labeled and unlabeled data together while not really losing any speed. So on the left-hand side, we have the model that we would have learned if we had only used the labeled data. On the right-hand side, we have the model that was learned using semi-supervised learning on all of the data. you can see that in addition to getting better accuracy, that we're learning decision boundaries that seem more reasonable. Here, the decision boundaries seem very sharp and kind of weird, whereas here they're very smooth. That these smoother decision boundaries are easier for us to believe and more likely correspond to real phenomena. So, next, Pomegranate can be faster than SciPy. That if we, say, have 2,000 samples from a 2,000 dimensional matrix, and we want to calculate the log probability of them, we can use SciPy, and that takes around 1.67 seconds, or we can use Pomegranate, and it takes around 800 milliseconds. If we have a pre-created object in Pomegranate, then it only takes 216 milliseconds in order to do that, to calculate the log probability. And the reason is because Pomegranate uses aggressive caching across all of its models. Here on the top, we have the normal equation, the calculating the probability given a normal distribution. If we take the log of it, it decomposes into these nice two additive terms. But you notice that this log of square root of 2 pi sigma doesn't depend on your new data, but it takes up the most of your computational cost. This side is just, some additions and multiplications. That's not a big deal. But here, this square root and this log, these transcendental functions take way longer. And so if we simply cast this value when we create the object, we now have some alpha constant that's calculated initially. And then to calculate the log probability of some new data, all we have to do are these additions and multiplications. So I think that at this point, I should give you a real-world example that I think that most of you can really relate to. And that is the example of Gossip Girl. That in college, my girlfriend was interested in watching Gossip Girl with me, and I decided to watch the first episode with her. It seemed as though the gist of the story was that there were a group of angsty Manhattan teens running around, hooking up with each other, and in general, disappointing their parents. In the background, there was this enigmatic character known as Gossip Girl who sent out these text message blasts just in time to stir up trouble with the main characters. This is, of course, trouble and drama that could have been solved if any of these characters talked to each other like human beings. What they decided to do instead was to glare at each other menacingly from across the room to let them know that they were angry. So this is an example of the first blast. Spotted, lonely boy, can't believe the love of his life has returned. If only she knew who he was. But everybody knows Serena, and everybody is talking. Wonder what Blair Waldorf thinks. Sure, they're BFFs, but we always thought Blair's boyfriend Nate had a thing for Serena. What a shitty thing to say to anybody, much less to say it in a text message to everybody. So, of course, I was immediately hooked. So this was the blast at the end of the first episode. Why'd she leave? Why'd she return? Send me all the deets. And who am I? That's the secret I'll never tell, the only one. So I took this as a challenge, not wanting to let my girlfriend know that I was actually really interested in continuing to watch the show. I decided to take this as a challenge and say, I'll only continue watching it with her if she helped me figure out who Gossip Girl was using data science. So what we decided was to go through each of these blasts and encode them as either being for or against somebody's agenda at the time. For example, better lock it down with Nate B, clock's ticking. This is in favor of Nate's agenda because he wanted to be with Blair, but it's against Blair's agenda because he was being non-committal because she didn't know how she felt. This just in, S&B committing a crime of fashion. Who doesn't love a 5-finger discount, especially if it's the middle one? For those of you not in the know, a 5-finger discount is theft, so this is outing 2 of the main characters for stealing, so it clearly works against both of their agendas. Now, as a data scientist, what you end up with is a matrix where each row corresponds to a blast, each column corresponds to the characters, and the values are either 1 if it was for their agenda, 0 if it was unrelated to their agenda, and -1 if it was against their agenda. So you might initially just want to take the sum of that and see what happens. If you do that, some interesting things pop out. Like, for example, Blair on the left seems least likely to be Gossip Girl since she has the most shit said about her. However, it seems like nobody is unscathed, that we would have liked if one person was clearly being helped out a lot, but everybody is in the negatives. Unfortunately, nobody is the most unscathed, with there being a 3-way tie between Dan, Nate, and Vanessa. So, at this point, we either could have turned, we could have either given up, or we could have turned to probabilistic modeling. And that's, of course, what I did. So we turned to the beta distributions. Beta distributions model rates, and so they're a distribution that are between 0 and 1. The most canonical example is trying to figure out the probability of getting heads when you flip a coin. And so here, before you flip the coin at all, you get the blue distribution. You know nothing, and so it's just a uniform distribution. It could be any parameter. Then you flip the coin twice and you get two tails. And it says, okay, well, since I've seen no heads, it seems most likely that I can't produce heads, but there's still a chance that the parameters can fall within any of this space. Then next, we flip the coin again and we get a heads, and the probability of never being able to see heads drops immediately to 0, which makes sense because we just saw heads. So as you collect more data, the variance of this distribution decreases, and you get something which converges to around a normal distribution around 0.5, indicating that this is a fair coin. So we applied this to the Gossip Girl data, where we tossed out the 0 label and simply said that if it was in favor of somebody's agenda at the time, that was heads, and if it was against their agenda at the time, that was tails. This is after season 1, where you can see much more distribution than before. It seems like Dan is the most likely to be Gossip Girl according to this, and Jenny is the least likely to be Gossip Girl. Interestingly, Blair seems like she's towards the middle instead of way towards any of the sides. We do this after each one of the seasons, and we see some interesting things. The first is that these distributions do seem like they're converging, which makes sense that given more data, the variance of them are all going to decrease. Unfortunately, it seems like they're kind of decreasing towards each other. One of the interesting things that pops out is that Blair is kind of in the middle here, and that indicates that while there was the largest difference between negative things and positive things said about her, she was just involved in so many of Gossip Girl's blasts that 30 isn't a big deal. Like, for example, the difference between 1,000 and 30 and 1,000 is not nearly as big as the difference between 2 and 32. So this kind of messes with the idea that the producers didn't really know exactly who was going to be Gossip Girl until the show was abruptly canceled for who knows what reason. And then they just decided that one of the characters was going to be it. But perhaps there was some signal in the noise, because, spoiler alert, Dan was Gossip Girl, and according to this model, he is the most likely one to be Gossip Girl. So, thank you. So getting back to Pomegranate, one of the models I'm going to describe the flexibility that Pomegranate provides for is naive Bayes. That typically we think of naive Bayes as like Gaussian naive Bayes, where we have the Scikit-Learn implementation on the right-hand side of this decision boundary and the Pomegranate one learned using this code on the left-hand side. If we model each one of these distributions using a normal distribution, we get these kind of ellipsoid boundaries here, where we're separating out the magenta points from the cyan points using this boundary. The math behind it is pretty simple, that you have the posterior is equal to the likelihood times the prior divided by some normalization. It doesn't particularly matter, except that this likelihood term, it can be calculated using a full multivariate function. In that case, it's called a Bayes classifier, but the naive part of naive Bayes assumes that each one of the features is independent from each other. So what's going on here is that if they're independent from each other, then this likelihood term breaks down into the product of probabilities according to each feature. If that's the case, we don't need to have the same probability distribution along each feature. We can use any probability distribution, and this has a lot of real-world implications. For example, imagine we have some sort of signal data like this, that there are 3 main aspects that would correspond to each one of these segments if we want to classify them as being either magenta or cyan. We could take the mean of each one of these segments, we would take the standard deviation of each one of the segments, and we would take the duration of the segments. If we look at the distributions of each one of these features, they aren't all Gaussian. The mean is probably Gaussian, and that makes sense. The standard deviation is clearly not Gaussian because it has to be limited to be positive. A normal distribution is going to say that, since it's symmetrical, that there is some probability of it being negative, but it seems here like a log normal distribution or a gamma distribution is more likely going to model the data well. Likewise, durations are very commonly modeled using exponential distributions, and that seems to be the case here, where you have some exponential decay going downward. You wouldn't want to use a Gaussian distribution for each one of these features. And this has real-world implications. Here's the code to train just the simple Gaussian naive Bayes in Pomegranate. Here's the same code, but for Scikit-Learn. And here's the code for Pomegranate using the appropriate distribution to model each one of the features. You can see here that we get around an 80% accuracy using just normal distributions, where we get an 84.4% accuracy using the appropriate distribution. We don't have to clean the data at all. We don't have to get new data. We don't have to transform the data. We simply have to use the appropriate model in order to model our data. This additional flexibility comes at no additional computational cost. That here we increase the number of dimensions with random distributions from Pomegranate versus just the Gaussian naive Bayes and Scikit-Learn. It seems like it takes around the same time. In part, this is because naive Bayes classifiers are super easy to train regardless. Sometimes, though, modeling your features independently isn't the right thing to do. Here we have some sort of blobs, but they're tilted blobs, where as you increase on the x-axis, you also increase on the y-axis. That if we just use a naive Bayes model on the left-hand side, we get kind of a decent decision boundary, but clearly it's not the best one. Pomegranate also implements Bayes classifiers, which is the generalization of naive Bayes to not assume that each one of the features is independent from each other. If we use multivariate Gaussian distributions as our emissions instead of these univariate distributions, we can learn decision boundaries that look like this, that nicely split these two things apart, and again, get a much higher accuracy simply by using the more appropriate probabilistic model. Likewise, we can also use, there's no reason we have to limit ourselves to these simple distributions. We can use mixture models if we'd like. That on the left-hand side, we're using a single multivariate Gaussian distribution to model our data. On the right-hand side, we're modeling our data as a mixture of two Gaussian distributions. And we get this kind of like Pringles man looking phenomena going on here with the two eyes and the mustache. But it's identifying that there's this cluster of points here, cluster of points here, cluster of points here, and so on. And so it's able to learn that this is probably a more appropriate decision boundary than that. Again, there's no reason mathematically that you can't use these complicated models as probability distributions because they are probability distributions. So lastly, I'd like to talk a little bit about Bayesian networks, which are also implemented in Pomegranate. Here's an example of a very simple Bayesian network over 3 variables: rain, whether or not it rained, whether or not you turned the sprinkler on, and whether or not your grass was wet. This is a pretty simple example, and if each one of these nodes corresponds to a variable, and each one of the edges corresponds to a dependency statement. The lack of an edge corresponds to a conditional independent statement, not explicitly an independent statement. So what this is saying is that if it rained last night, it's more likely that your grass is wet, but it's also more likely that you didn't run your sprinkler. If you did run your sprinkler, though, it's likely that your grass is wet. So this is just an example of a really simple one. There are 2 main tasks when it comes to Bayesian networks. The first is performing inference. And generally, the reason that people use Bayesian networks is because they're very flexible when it comes to what data is present and what data is missing. Many classic machine learning algorithms say, here are my features that are always present, and I'm going to predict something which is always missing, your like Y label. With Bayesian networks, not only can you have widely varying amounts of missing and available data, but these can differ on a sample-by-sample basis. It'll simply use all of the available data in order to get better estimates for the missing data. So this is incredibly flexible. The second is learning the dependency structure from data. And this is very popular when it comes to like academic research and when you're trying to build causal models, that what you want to do is learn which variables are related to each other, which ones influence each other. And so I'm going to focus the rest of the talk on that. There are 3 primary ways that you would do structure learning. The first is search and score. What this basically does is you go through all of the possible Bayesian networks, you score them according to the sum objective function, and you see which one does best. The second is called constraint learning, where you first perform some sort of statistical tests to identify which pairs of variables are unlikely to interact, and then you don't bother checking them. Last are some heuristics, because both of those methods take a lot of time, and frequently what you need is a good but not necessarily optimal Bayesian network, and you need it fast. So there are a lot of heuristic algorithms that have come out recently. Not recently, like decades ago. So I guess that's recently, depending on who you are. As a young whippersnapper, that's most of my life. So Pomegranate currently supports search and score methods for exact learning and some heuristic methods. The 4 ones that it supports are there are 4 methods that it supports. There's the exact learning method. There's the exact learning method that is, the exact learning method, as you might imagine, takes a lot of time. There are a ton of directed acyclic graphs that you would want to go through and try to find the best one. It actually takes a super exponential amount of time. You can see that here in the blue, that when you've got into 6 variables, it already takes 1,000 seconds. When it gets to like 8 variables, it's probably totally not going to work at all. And unfortunately, most problems have more than 8 variables. Then, somewhat recently, in around 2015, a dynamic programming algorithm came out, which reduced it from super exponential to simply exponential time. And you can see that here in the red. I have to admit that was the first time I had heard simply exponential heard in like a good way. But I suppose that if you're going up from like 8 variables to, in this case, you can get up to maybe 20, 30 variables, that's a significant improvement. So Pomegranate has this dynamic programming algorithm implemented both as a shortest path formulation and as an A-star search formulation, where the A-star search is still exponential in time in magenta, but is slightly faster. Then I have a greedy algorithm that I developed over the course of implementing these. I haven't yet published it because I don't think the world needs yet another greedy Bayes-net structure learning algorithm, but it provides pretty good approximations. And the only reason, that's currently the default in Pomegranate, because I don't want people to kill their computers by not knowing that exact structure learning takes forever. Then we have Chow-Liu trees, which try to find the best Bayesian network that follow a tree-like structure. So each node can only have one parent, and that's pretty fast. On the left-hand side, you can see a speed comparison, where as we increase the number of variables, the greedy algorithm starts to increase around quadratically. The Chow-Liu tree is going to be super fast up to several hundred variables, and then we can test their performance where higher is better. You can see that the magenta and the cyan lines superimpose because they're the same algorithm, just slightly different. They're both exact algorithms, just slightly different technical details to them. The greedy algorithm does well, but not optimally, and the Chow-Liu tree does the worst, which makes sense because there are significant restrictions on it. Frequently, though, when you're trying to learn a Bayesian network, you have a great deal of domain knowledge. And this is the research that I was interested in telling you about before. That a while ago, Microsoft was interested in creating a diagnostic network. And what they did is they created this Bayesian network with 3 layers. The first is you had your symptoms here. You had low energy, bloating, loss of appetite, vomiting, abdominal cramps. In the middle, you had diseases or conditions like ovarian cancer, lactose intolerance, pregnancy. And at the top, you had mutations in the BRCA2 gene, BRCA1, and the LCT genes. If you're trying to learn the structure of this Bayesian network, you have a lot of domain knowledge that you'd like to incorporate. For example, you can't have edges going from genetic conditions to symptoms. You can't have edges going from symptoms to anything up here. That can provide a great deal of improvement because this is typically a simply exponential time algorithm. So this is an example of a constraint graph, which is the formulation that I proposed. What you do is you take each of your variables and you group them together into sets, and you define relationships between the sets. That when you're trying to do structure learning, you're saying, okay, well, diseases can have their parents drawn from genetic conditions, symptoms can have their parents drawn from diseases, and that's it. If you compare the time that it takes to do normal exact structure learning, discarding the graphs that don't follow the constraints versus using the constraint graphs explicitly, you get this comparison here, with cyan being exact learning, and then magenta being constrained learning. As you get to 18 variables, it's still taking less than 1/10 of a second. So, of course, I did what anyone does when they develop some new machine learning technique, and I tried to make money off of it. So I attempted to model the global stock market. What we did here is we looked at 3 markets: the Tokyo Stock Exchange, the Financial Times Stock Exchange in London, and the New York Stock Exchange. We looked at the opening and closing prices of these, but binarized to see whether or not it was an improvement versus the last price we saw. So there are a great deal of just time-based, the temporal constraints between these variables, that the opening prices in the Tokyo Stock Exchange can't be influenced by the opening price of the New York Stock Exchange because you haven't seen them yet. So here, the opening prices of the Tokyo Stock Exchange influence the closing prices of it, of course, but also the opening prices of the Financial Times Stock Exchange. Likewise, the opening price of the Financial Times Stock Exchange influences the closing prices of the Tokyo Stock Exchange, which hasn't yet closed when the Financial Times Stock Exchange opens, and so on. One of the important things that we discovered while pursuing this research on constraint graphs is that if you have an acyclic constraint graph like this, that the Bayesian network structure learning task takes only quadratic time instead of exponential time. And so even though we are modeling 140 variables, learning the exact Bayes net that fit those constraints only took 2 seconds. That's a pretty significant improvement. And here's a slice of it. I wouldn't look too deeply into the connections here because that's how I'm making all of my money, of course, and don't want to compete with you. But you can see that there were some dense connections here that I've learned. So this resulted in a paper that was published earlier this year. I would encourage you to take a look at it if this type of research interests you. So to get back to the main statement, Pomegranate is more flexible than other packages. It is faster, it is intuitive to use, and it can do all of its operations, fitting and prediction, in parallel with built-in parallelization. So, some news before I finish my talk. The paper preprint was put on arXiv yesterday. So if you're interested in learning about the design decisions behind Pomegranate and how that influenced its development and more features, I would encourage you to read the paper. This week, Pomegranate is now NumFocus affiliated. It was added to the list of affiliated projects a few days ago. Documentation, extensive documentation, feature-specific, frequently asked questions, and the API reference are all available on Read the Docs. I would encourage you to look at it more if you want to use any of these models. And lastly, tutorials are all available on GitHub, one for each of the models or main features. So you can see how one would use it in practice. So, thank you. I think we have some time for some questions. Yeah. Yeah, I don't actually know who's using it. I continually hear from people that they are using it, but I don't have a main repository of people who are. I'm not really sure how to answer that question. I know that there have been companies that have used it in the past.
Do you know how they have used it offline or like offline models versus online models?
Oh, no, I haven't really. Mostly that they email me to say like, hi, I'm from blah, can you add this feature? And I ask them, are you paying me for this? And unfortunately, the answer is typically no. Yeah. No, when you're learning the sufficient statistics, you don't have to make any assumptions about the data. You can learn a covariance matrix using sufficient statistics, and that's in fact exactly what happens when you're using the multivariate Gaussian distribution. If you are learning univariate distributions, then of course each one is going to be independent from each other, but that's a user-defined constraint. Any other questions?